He will talk about very deep roots and unexpected root growth.
Thank you. Hi, everybody.
Wait, Christophe. That's the presentation is not there. And try to locate yourself. There are some empty seats there.
Okay. Oh, sorry. I'm taller. Just in size.
Okay.
Hi, everybody. I'm Christophe Jourdan. I work in CIRAD. It's a French research institute working on agriculture, but focus on development. And we work in tropical countries. And I will present here, so I will report some unexpected wood growth and functioning at very deep, in very deep soil. Sorry, and I will try to know if these features are have an ontogeny origin or they are adapted to local stresses. So this is one. So plant roots exhibit huge rooting depths, mainly shrubs and trees. They explore very deep soil layer. It's not new. Old publication published by Canada in '96 show that these some plants can reach very deep soil layers, more than 50 meters. And they are usually in drought or arid conditions, such like desert or sclerophyllous shrublands or savanna. So deep root colonization, where I may ask some questions of for what functions, for anchorage, probably not, for nutrient uptake, as we have recently evidence that some specialized roots can be found in deep layers that can act as a safety net to catch some nutrients that leach from the upper soil layers. Other function, water uptake, undoubtedly yes. A lot of paper mention that. For what roles? Is there a strategy to survive during the dry season? Or is it an adaptive response to shallow plant root competition? So we may question about also about the impact of these deep roots on the carbon sequestration, also on the water balance, but also on the biogeochemical cycles. So why looking deeper? Usually when you observe the root system, you dig, at field of course. You dig usually a few centimeters, 1 meter, 2 meter, rarely more, for to study the structure, the architecture of the roots, or to study the dynamics with mini rhizotron, for example, here. But when we get all the root parameters into a model, we put the parameters that we measure on the topsoil, and we put together in a model, and we simulate the root distribution within the soil without wondering about the the depth condition. And we simulate here, for example, a 20 months old eucalypt, and we reach 5 meters deep. But when we observe this, the same the plantation here in the chronosequence in Brazil, the progression of the root front. There is something to show here? No. Maybe here. Here, the progression of the root front. And when we look at 20 months old plantation, the root front was found at 10 meters, so the double of what the model simulates. So we went to the conclusion that we need to study deep root dynamics in this condition. So I will present mostly the results coming from Brazil, from eucalyptus plantation in São Paulo state with moderate drought condition. So to go deep, you have to dig and to make some access pit to a great depth. So we went to 17-meter depth. Amandine will show you an interesting film how to go down there this afternoon. And we put on the wall of the pit several mini rhizostones. Here's a picture of what we found at 6 meter deep, for example, as an example. We get a huge amount of fine roots growing, and these fine roots are still remain 1 year later, and with the apparition of a new cohorts of roots here, that we try to follow here. 1 month later, this cohort exhibit a huge speed of growth, and they came across the image, which represent more than 25 centimeters here. So if we look the cumulative root length at that depth, we found an expected cumulative root length that be increased, that was more than the upper layers, of course, not the very shallow soil layer. So the cumulative fine root production at great depths we found at the first time as an artifact, or if there are a reason why at that particular condition, a specific root condition to exhibit such speed of growth. When we plot over a 2-year period the daily and the maximum root elongation rate, we were surprised to find that there is an increase in daily root elongation rate when we go deeper, and as a maximum root elongation rate we reach more than 3 centimeters per day. So we have a significant increase with soil depth. If we look at the mortality or the dead root production, as plot here with bars, as daily dead root length loss, here in the shallow horizon and here from 5 to 6 meter deep, we observe that the mortality occur whatever the soil water content. This is the first remark on the shallow horizon. The plot here is the relative extractable water. So even in dry season or in the wet season, you have mortality on the shallow soil layer. And when we look at the deep horizon, the mortality decrease, and it was not limited to the dry soil, but also when the amount of water was full. In another experiment in the same plantation, we harvest fine root with auger in 2 plantations at 2 years old and 4 years old, and down to 15 meter deep, where we reach the water table. We have TDR probes in the big pit, monitoring at the same time the water, soil water content. What we found is that at the 4 years old, the density increased on the topsoil, so it was what we expected. But we found an increase in the at 4-5 meter deep in the density of root, and also a little increase at the 14 meter deep. And what is interesting is that despite the fact of the low density of roots, we have a huge amount of water extracted from the soil layer. I have to mention that after 2 years old, the rains cannot refill the deep soil layers. All the roots uptake water coming from the rain. So the water extractable water here is extracted by this small amount of roots. To increase drought condition in this ecosystem, we set up a rainfall exclusion experiment with plastic gutters, and we, with the objective to remove more than 1/3 of the throughfalls. We installed this system from the seedling plantation, and we harvest roots down to 4 meter deep at 5 years old of the plantation, just 1 year before harvesting the plantation. And we are looking the carbon. First, in the bulk soil, here the carbon content in percentage. The bulk is the control is in blue, and the drought treatment is in red. So there is no difference between, there is no treatment effect, and there is an exponential decrease of carbon content in the soil, as we expected. But what I want to stress out here is that, as a recent paper said that it was interesting to look at the carbon at more than 30 centimeter deep, up to 1 meter. And here, if we compare to the wall profile, 1 meter is not enough to look at for the carbon sequestration. If we look at the nitrogen, we have the same trend here. So considering the wall soil profile, down to 4 meters here, deep bulk soil layers contain more than half of the carbon and nitrogen stocks, at least in the Brazilian site. If we look now in the rhizosphere, so the control, we have a slight but significant rhizosphere effect with an increase here. And in the drought effect, we have a double accumulation of carbon, organic carbon in the rhizosphere, and this amount reached 3 times at 4 meter deep. For nitrogen, we have the same trend, but with lower value. So accumulation of carbon and nitrogen within the rhizosphere coming from exudates is enhanced by threefold reduction, and particularly at great depths. Concerning the available potassium, we have the same trend with a significant increase within the rhizosphere for the whole profile, particularly at depths. And in drought condition, we have 7 times more potassium in the rhizosphere than in the bulk soil. The pH also show an acidification, not in the topsoil, but in the deeper region. And with drought condition, this acidification was increased. So accumulation of protons and available potassium within the rhizosphere, particularly at great depths, and this was enhanced by drought condition. And these features might increase the disponibility of exchangeable potassium at great depths and during dry periods through weathering processes. Concerning morphology, we found mycorrhiza at the big depths, at great depths, 7 meters here. So I invite you to visit the poster number 22. Some particular root tips with hairy root tip, I don't know the name, we found at 15 meter deep with highly branch, not highly branch, but with high density of root hairs that live for a long period, as we can find the root hair here in the differentiated root, branched root. Concerning anatomical features, here for juvenile fine roots with the same diameter, we compare shallow roots to deeper roots. We saw that we have a huge parenchyma at great depths, so it could be adaptation to higher saltwater content. And if we look at the differentiated fine roots, we can see that we have fewer but larger xylem vessels at depth, in deep roots that can suggest and improve water transport to in that deep soil layer. So to conclude, I want to give you take-home deep message for the. So deep roots exhibits higher elongation rate and lesser mortality rate, and that can lead to longer lifespan, shorter turnover. So the lesser root density, but the sum on all the whole soil profile amount non-negligible root biomass proportion to uptake deep water. Higher organic carbon, nitrogen, and available potassium concentration within the rhizosphere, which is quite original. And this was increased under drought condition, and particularly at great depths. There is change in anatomy with fewer larger xylem vessels, and morphology with higher density of long-lived root hairs. So our hypothesis is whatever the plant species and ecosystem with or without drought condition, we check this with coffee trees in Costa Rica in tropical humid conditions, and also in walnut trees in southern France where we have a southern drought. So this suggests a territorial strategy providing access to resources at great depths, suggesting an ontogenic determinism in addition to the effect of the environment on the deep fine wood colonization. So our perspective, our group is working on the fate now on the deep carbon coming from exudates and the fine wood litters, particularly at great depths, and its impact on the carbon sequestration. We'll also study the biotic interaction of the soil and root interface at depths, studying the mycorrhiza and microorganism interaction with roots. And also, we investigate the hydraulic and nutrient lift from deep layer in agroforest systems. So, deeply, thank you for your kind attention.
Thank you, Christophe.
Sorry.
We